Hello, everyone. Come on in. Another exciting day of electricity and magnetism. Got about a minute before class starts. Anybody have any questions? Watching my video the other day, I noticed I kept doing like this. What am I, ADD or got autism or something? I was acting like a nut job through the whole class. Sorry, I don't know why I was doing that. I don't think I've ever done that before. But anyways, if that bothered you, I apologize. I was like, I definitely had something going on, which I actually do have ADD, so it's perfectly normal for me to fidget and stuff like that. I've just never done it in circles like this before.
Getting
Right.
out those first day jitters.
Yeah, I guess that's what it was. It's been so long. Well, today we're going to jump right into using vectors. Remember, I told y'all in the last, in the first module, there's a module 0 for week 0 that's supposed to be stuff that you're supposed to know how to do. So having taken the chapter on gravity, or having done that, or at least went through it roughly with your 241 class, you probably already learned how to take a formula for a force and then convert that to a vector. That's mainly what you got to do throughout this whole semester is convert diagrams and drawings with formulas that just give you magnitudes, and then you got to do proper more or less look at the shadows cast by the vector on the x-axis and the y-axis. The shadows cast on the x-axis, of course, is the x component of the vector, and the shadow cast on the y-axis is the y component of the vector, and you got to assign them signs. That's the way I do it. I don't force myself to use a standard angle and use angles like 276 or something like that. I just always use the angle closest to the or the angle between the vector and the nearest axis, and then I look at it, decide what signs the x and y component have. So that's the way I'm going to practice it. I've got a couple of examples worked out already that I prepared to do, so I can sort of fly through them, and I chose numbers that were nice so they'll actually work out without me having to use a calculator. Of course, to do that, you sort of need to know some special triangles, which I suspect you guys already know to some extent, hopefully from your pre-calculus or trigonometry course. Today's class, of course, is PHY 242. I'm not showing you the notebook yet. I'm just wanting to write the date before I forget. 242 N05B, and the date is 01/12/22. So let's get started with sharing my screen so I can show you a typical example. So I've written them up in Word, and I didn't want to waste a lot of time drawing diagrams, so I describe them and then I'll just draw the actual diagram during class. So the first example we're going to work on, and I actually have others too that I'd already worked out, but I didn't get time to type up, so it's no big deal. Example 1, 3 charges are located as follows. There's a charge Q1, which is 0.111 microcoulombs. Those of you who aren't that awesome at arithmetic, I want to point out that that's essentially 1/9. Okay, 0.111 is 1/9, so that'll come in handy. But it's at the position x equals -20.0 meters. Q2 is 40, in this case, millicoulombs at x equals 0.0. Evidently coulombs is what I decided to put that axis dimension in, which is absurd. But anyways, yeah, it's meters. So that's where the Q2 is. And then Q3 is 0.333, which I hope you all recognize what that is as a fraction. That might come in handy as well. And that one's located at 10 meters. So let me draw the diagram. So we'll call this example 1, and I'll draw the diagram, then I'll show you the paper. So I just want you all to have time to write that down or whatever. So in this case, I've got Q1 that's going to be 0.111, and that was microcoulombs. And then about 20 meters away, I have 40.0 millicoulombs, and that's Q2. And this Q1 was positive. By the way, this is supposed to be a negative on the 40. Not that it matters too terribly much, but the main thing is I wanted them to be attractive, so I made it -40. And then the last one's only 10 meters away, and that's Q3. And Q3 has a magnitude of 0.333 positive microcoulombs. So I'll go ahead and draw my diagram. I've got it drawn as if it's an x-axis right now. And there's the y-axis going through the 0.0. This is through the 10.0, and this is through the negative 20.0. Now I'll go ahead and turn on my document cam. So you can see what I've done is I've drawn the diagram. What I often like to do is I like to use colored pens to demarcate the directions of vectors, because then when I do it, I can use things like, red for negative and green for positive, just like a red light means stop and a green light means go. So what I'm asking for in this case was the total force on Q2. Actually, let me double check that. I'm going to share again just to make sure I'm doing the right one. What I'm asking for is what is the net force expressed as a vector on charge Q2. Okay, so I was remembering correctly, which is yay for Mr. Younger. He didn't have a senior moment. So what I will tell you is that vectors add, or forces add, electric forces add, just like forces in general. So it's a vector quantity. So when I say F3, I use that to denote the total force on, actually, since I say F2, I use that to denote the total force on charge 2. Okay. Now, what that means is I'm going to add up all the charges acting on it. In this case, it's only 2, but more generally, you would do something like this. You say from I equals 1 to n number of charges. In this case, it's n equals 3. All right, so I goes from 1 to 3, but you also can't count something applying a force to itself. So I wouldn't want 2 in there. So that's the fancy way of writing it with a summation, when in general it would just be I equals 1 to n, and you exclude one of them, say m or something like that. And now the way I write it is the force on such and such an object, which in this case would be 2, due to I. Okay. So what that means is F2(1) plus F2(3). So that's really all I'm saying, is I'm just taking the other forces. So I'm wanting to know the total force on this. I'm going to calculate what the force on this one is due to this one. And I call that F2(1) because my nomenclature is the first subscript is the object is acting on, and the second subscript is the one that's doing it. And then F2(3) is the force on 2 due to charge 3. So I just need to compute those. What I have is Coulomb's law, which says that F is equal to K Q1 Q2 over D squared, where D is the distance between them. Okay, so I'm going to work out the magnitudes and just realize right now to the right is the positive direction. This is a positive charge, that's a negative charge. So in fact, this charge feels compelled to be pulled that way. So what I would do is I would write a red vector symbol, or excuse me, a green vector symbol in this case, since it's in the positive. I literally just looked at a red marker and said red because I was looking at it. So this will be the force on 2, if you will, due to 1. It's literally going to be pointing to the right. Maybe I should have drew it over here, but I liked it being attached to charge 1, so you know which one I was talking about. Now this one, on the other hand, when I do the force on 2 due to, oh, actually, technically speaking, I have to say that's the opposite direction, since it's a force on 2 due to 1. I literally wrote it backwards. So the force on 2 due to 1 is actually pulling it that way. So I really should have used red. Maybe that's why my brain was telling me to use red. I don't know. I don't think my brain's that much ahead of me, but it may be. I did tell you I've got ADD, so I'll put that force like that, really big, and that is in fact F2(1). And what it means is that this vector is lying all along the x-axis, so it only has an I hat component. And in this case, it's pulling Q2 to the left because they're oppositely signed, right? That's why I chose that direction. Like charges repel, unlike charges attract. These two are unlike, so Q2 is being compelled to go that way. Okay. Now, what I also know is that this one's positive and this one's negative. So this force over here is also tending to pull Q2 towards it. So in that case, I really do have a green vector. And this is the force on 2 due to 3. Okay. That's what I mean by just working out the magnitudes of the force and then using the drawing to figure out the directions and signs of the coefficients and all that good stuff. So now what I'm going to do is calculate F21. F21 is going to be 9.0 times 10 to the 9th. I'm only going with 2 sig figs just to make the life a little easier. And that's Newton meters squared per Coulomb squared. It's going to be times the charge of, notice I'm leaving off the sign here. It's the charge of particle 2, which is 40.2 times 10 to the negative 3rd. That's what a milli means, coulombs. And then I'm multiplying that times 1, which is 0.111. Again, though it didn't matter because it was positive, I did not write down the signs. I never want to include these signs in here. They're just going to make things nasty. But it's a microcoulomb, so I'll say it's times 10 to the negative 6 coulombs. And then, of course, the distance between them is 20 meters. So that's going to be 20.0 meters, and that's going to be squared. Okay. I think you can sort of see what I was talking about. Since that's 1/9, the 0.111 is 1/9. That exactly cancels out with this 9. So that's why I chose that number so nicely. And since this is 10 to the negative 6 and this is 10 to the negative 3, those two guys, 10 to the negative 3, 10 to the negative 6, cancels out with a 10 to the 9. So all I'm left with is 40 over 400. So 40 over 400 is 0.10. And the units, of course, turn out to be just plain newtons in this case. So the vector F21, since we've already established that it points to the left, it's going to be negative 0.10 newtons in the I hat direction. Remember, I hat is a unit vector. Literally, its length is 1, not 1 meter, not 1 newton, not anything. It's just 1, okay? And it points in the positive x direction. So by that negative being there, that means it's going to point this way. All right, now I'm going to do the same thing for F23. That's going to be 9.0 times 10 to the 9th newtons meters squared per Coulomb squared. I would write those units like this every time until you're really, really comfortable with it. And I would really try to do it on tests just to keep you from making careless mistakes. Like sometimes you'll calculate the electric field and the units will come out as newtons because you used the wrong formula. But if you were paying attention to the units, you would have caught that. So now I got to take the charge of the number 2 particle, which is 40.0 times 10 to the negative 3 coulombs. And then of the 3 particle, which is 0.333 times 10 to the negative 6 coulombs. And then this one's going to be over 10.0 meters squared. So what you can see in this case is the 0.33333 cancels out with this, just leaving a 3.0. Because the 0.333 is 1/3. Of course, the 10 to the negative 3rd and the 10 to the negative 6 do cancel out with this 10 to the 9th. So that's pretty nice. So what I end up having is 3 times 40, which is 120, over 10 squared, which is 100. So that's what's going to be, in fact, equal to 1.2 newtons. And we flipped out the bottom of the page. So that should be 1.2 newtons because the 40 times 3 gave me 120. I divided that by 100. That gave me 1.2. Now I can write the actual vector, F21 vector, or excuse me, F23 vector. In this case, remember we said it's going to pull Q2 to the right. So that's going to be a positive 1.2 newtons in the I hat direction. So F3 as a vector is, or excuse me, I keep writing F3. F2 as a vector is just going to be the sum of those two. So that's negative 0.10 newtons I hat plus 1.2 newtons I hat, which equals 1.1 newtons I hat. In other words, the net force is in fact pulling it to the right. And that that should make some sense, because this 0.3333 charge, that's 3 times stronger than that one. So it should be 3 times the force if they were the same distance away. But it's also twice as close, so it should be 3 times 4, because it's twice as close, which means 2 squared would be 4. So you should actually get 12 times bigger. And in fact, that's exactly what we found. 0.1 times 12 is 1.2, which is exactly what we had there. Okay, that's just the nature of a Coulomb's law type formula that says that the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. If I increase the charge by a factor of 3, I increase the force by a factor of 3. So in going from 0.11 to 0.33, I'd expect it to go from 0.1 to 0.3. But I also change the distance. The distance is inversely related. So by decreasing the distance, I actually increase the force, but not by a factor of 2, but by a factor of 2 squared, which is 4. So 4 times 3 is 12. 12 times 0.1 is 1.2, and that's exactly what I got. Okay, so you could have in principle done that right off the bat, but like I said, I want to show you how to deal with vectors. Now, here's the kicker. That's pretty much the only example I'm going to give you using that form of Coulomb's law. Everybody despised, in some sense, Coulomb's law, just like everybody despised Newton's law of motion, or excuse me, Newton's law of gravity. The problem was in Newton's law of gravity, and the problem is in Coulomb's law of motion, is that it appears like, say, the sun is reaching out over some distance and tugging on the earth, and you can't find any kind of tether or chain or anything pulling on it. So it's like what they call it is action at a distance, but it's like magic, and everybody was bothered by that. But and even Newton was bothered by it, but he knew there wasn't anything he could do about it. But he also knew that using it, assuming it was happening, he could figure out some big problems. So like we could have used Newtonian mechanics, and it would have just done just fine getting us to the moon and back. Our time instruments would be off a little bit and stuff like that, but the way they were monitoring it, they would correct it all the time, so that wouldn't have been a big deal. So it is okay to use, but what they did instead of worrying so much about it, actually a guy by the name of Maxwell did it, but before him, Michael Faraday was suggesting it was almost as if something was created around a charge, sort of a aura around a charge, and that thing would be known as a field. And what do we mean by fields in physics and mathematics? Is an assignment of some quantity to every point in space. So if I say a temperature field, you can imagine here's a point X, Y, Z in the coordinate system that you made up for this particular room. And if I could measure the temperature right there, you would say X equals 3 meters, Y is 2 meters, X is 1.4, I mean, Y, Z is 1.4 meters. And then the T value there is 20 Celsius, okay? Something like that. If you do that for every point in a huge chunk of space, then you've got a temperature field. In this case, we're going to have something called an electric field. And not only is it going to be like temperature where you have a number, you're actually going to have a vector associated with every point in space because it's a vector field. So that's what a field is. And it's the same wording we've been using since we watched Star Trek and Star Wars. When they talk about force fields and stuff like that, that's really all it is. It's imagining as if the space is permeated by something that we can't necessarily see, but does have the ability in this case to apply a force to something. So how would you go about doing that? Well, mathematically what they did is they imagined instead of having two forces on the same plane of existence, they would do something like this instead. So instead of thinking about F equals K Q1 Q2 over D squared, like this, where you had a charge Q1 and a charge Q2, they said, let's think of one of these sources as one of these charges as the source, and the other as the particle that's experiencing the force. So instead, you go, the electric field is going to be defined as the force, the same force we had here, divided by the charge experiencing it. So what we're going to do is we're going to say instead that this charge over here is special. It's the source of the E field. It's not really special. It just happened to be the one we chose to be the source. And then over here, you have a charge Q. So we're taking basically Coulomb's law and dividing out one of those forces. Now, in principle, this charge right here causes a field itself, right? Because when you make the argument that one charge can cause an aura around it, then all charges can make an aura around it. So in principle, what they do is they say, I want to take the limit as Q approaches 0. And that's really how they implement it in reality. So I'll soup it up a little further, write this limit as Q approaches 0 of F over Q. And now we have the electric field at P equals KQ over the distance squared. And the distance squared is really the distance from here to here, the center of charge for Q and the center of charge for little q. So that's what that distance d is. Okay. So just by doing this, we have this nice little formula. And in fact, it still relates to the original formula. I said E equals F over Q. So if once you have the electric field and you want to actually know what the force that little charge is feeling, then all you have to do is multiply the electric field times that little Q. So that means the force will just be Q times E. And this point right here, by the way, would now be called P. So that's why I did that little scripty P there, is just to let you know, by eliminating that one Q, you don't actually have to have a charge there to do anything. So I would rather call it the force at P, or excuse me, the electric field at P. These are completely consistent with the equations your book gives you. I'm going to derive something more fancy for it later. But right now, I'd like to work another example so you can sort of make sense of this. So let me share my screen real quick. Pull up our second example. So it says in example 1 above, assume Q1 and Q2 exist only. So in other words, we're ignoring Q3 for part A. What is, I don't know why I wrote what that is, what is the electric field at Q1 due to Q2? So this is example 2, part A, and we want to know the electric field at 2 due to 1. Okay, so I'm going to use the same notation again. Now that you've seen that, you notice that B, I'm going to say, okay, well, what's the electric field at 3 due to 2? So that one's going to be 3, 2. Okay, so that's what they're wanting to know for part A and part B. And then part, I should call it C, but there's no symbol there. I tell you to use F equals QE to compute F32, and then use Coulomb's law to compute F32. So that's a very typical type of problem we'd want to do, and it should help explain to you what we mean by making an electric field out of a force equation. So we have the same drawing as we had before. We still got that set up, but for part A, we're ignoring this guy. Okay. And we're acting as if, since we want to know the electric field on 2, we're acting as if we want to know the electric field at that center due to that guy. So what I'm going to say is E21 equals E at the origin. And it's going to be 9.0 times 10 to the 9th newtons meters squared per Coulomb squared. And it's going to be, in this case, we only have the source charge, which is a 0.111 times 10 to the negative 6 coulombs. And then we're going to divide it by 20 meters squared. And what we have to notice is which direction is the electric field? Well, the direction of the electric field is defined. Now, this is an important sentence, everybody. The direction of the electric field is defined to be the direction in which a positive charge would be compelled to move. So if I put a positive charge right here and we just had that guy over there, then I'd expect this charge to move that way. So the electric field must be in the I hat direction. Does that make sense to everyone? Yeah, if you put a positive charge there, ignoring these two that are there and just paying attention to the source charge, that would be compelled to move to the right. So it point in I hat direction. So once I count this magnitude, calculate this magnitude, all I got to do is multiply it by I hat and I have the vector. Okay. So this is 1/9 times 9. This is 10 to the 9th times 10 to the -6. So I basically get 1 times 10 to the 3, which is 1,000. And that'll be 1,000 divided by 400. So 1,000 divided by 400, you could say 1,000 divided by 4 is 250, and then you divide it by 100 and you get 2.5. So I'm going to say this is actually about 2.5. Anybody want to double check my math there? 9 e to the 9 times 0.1111. Actually, it's only 3, but e to the -6 divided by 400. Yeah, I get 2.5. And notice the units now, since I had a Coulomb squared down there, only one of these are canceling out. So this unit is newtons per Coulomb. And that's one of the units we use for electric field. Later on, you'll find out that it's also volts per meter. So that's kind of interesting. And like I said, once we cover voltage, that'll make more sense to you. So the electric field, E21, is in fact equal to 2.5 newtons per Coulomb in the I hat direction. So that's part A. Does that make sense to everyone? Part B, we're going to say E32 is again 9. I'll leave off the units this time for space. 9 times 10 to the 9th. Again, in this case, we're using the charge other than the middle one as the source. So we're using the 1/3 microcoulomb. So it'd be 0.333 times 10 to the -6 over, this time we're only dividing by 100 instead of 400. So what I end up getting is this 1/3 cancels out with that, leaving a 3. This 10 to the -6 cancels out, leaving a 10 to the 3rd. So I got 3,000 over 100, which should be just 30. Newtons per Coulomb. I want to double check my math because I am an idiot and this happens a lot. Okay, so we're going to do 0.333 e to the -6. And then I'm going to divide that by 10 squared, which is 100. And in fact, I do get 30 newtons per Coulomb. So in this case, this guy here is positive, and we want to know the electric field here due to that guy. So which direction should the electric field point in this case? The electric field that, exactly, Samuel, sorry. Yeah, so this positive charge would compel a positive charge here to go that way. So this one's going to be in the negative direction. So I'll say E32 is actually equal to -30 newtons per Coulomb in the I hat direction, but the negative, of course, fixes that. All right, any questions on that? Notice the electric field was somewhat affected as well. It's a difference of a factor of 12 like we had before. So if I multiplied 2.5 times the 12, basically, I should get about the same thing as I got over here. 2.5 times 12, that's 12, plus 12 is 24. Or yeah, that's 2.5 plus 10 times 2.5 would be 25. And then 0.5 times 2.5 be 1.25. Yeah, something like that. Anyways, They should work out. All right, so that's what happens when you fall off the beaten path. All right, now that we had that, we had this other part of the question, which was really, let's show you the screen again. It's really wanting to verify what the electric field equation gives you in terms of what Coulomb's law gives you. So I've done parts A and B. So what would be called part C and maybe D is use F equals QE to compute the electric or the force on 3 due to 2. And actually, I think my notation's backwards there. That should be the force on 2 due to 3. Yeah, that's exactly what I meant. The force on 2 due to 3 and the force on 2 due to 3. Because remember, we were calculating the electric field at location 2. So it doesn't make any sense to talk about the force on 3. So now that I can do that, I'll say, all right, well, the force on 2 due to 3 is just, notice we use the source as if it's 3. So the one I got left is the charge Q2. So I should have to multiply Q2 times E to 3. That's the electric field at 2 due to 3. And what did I say one here? Oh, this is where I went backwards there again too. I think that's why I had that number wrong, was I had written it down wrong when I solved it. It should have been 2, 3 here. Y'all might want to correct that. That's at 2 due to 3, not at 3 due to 2. And that means this one's got to change too. Sorry about that, guys. It's just terminology, but if you're using the terminology, I don't want it to go bad. So me making those mistakes is not helpful. So again, I should just take this negative 30 newtons per Coulomb and multiply that by Q2. So in this case, we know Q2 is 40. And notice this is a case where you could use negative. I see that Q2, that E23 points in the negative I hat direction. And I know that the charge Q2 is negative. So that'll force it to be in the positive direction. And that's exactly what you want, because that's the direction the charge Q2 would actually travel. So in this case, you might actually want to use it because we have the negative sign there. So I'm going to say this is 40.0 times 10 to the negative third coulombs. And I'm going to multiply that by negative 30 newtons per coulomb I hat. And now what I get is I can put vector symbols on top of them. And when I do that, I get 40 times 30. And of course, 4 times 3 is 12. So this would be 1200 times 10 to the negative 3, which would be positive 1.2 newtons, okay, in the I hat direction. Now, I said you need to compare that according to Coulomb's law. Well, guess what? We already did that for Coulomb's law. The force on 2 due to 3 is the same as the force on 3 due to 2 by Newton's third law, right? For every action, there's an equal but opposite reaction. So if I look up here, 2, 3 is 1.2 newtons. So we see that is exactly consistent with Newton's law, or Coulomb's law, excuse me. And this is sort of the answer to C. And the answer to D is F(2,3) equals K Q2 Q3 over D squared, which equals 1.2 newtons in the I hat direction. And that's a check. Okay, does that make sense to everyone? Just because I'd already done it in example 1, I already knew what Coulomb's law gave me, because in fact, I thought I'd calculated the other one 3-2, but in fact, I had calculated the correct 1-2-3. So I didn't even have to use Newton's third law. Any questions on that? I'm kind of blowing through it fast. All right, well, that one doesn't necessarily show the vectorness of it. It does, in that I'm getting you to use the I and J notation and stuff like that. And I showed you how you sort of use the idea that like charges repel and unlike charges attract. but I didn't really force you to do any vector components or anything. So I really need to do that. To do so, I'm going to introduce, again, an electric field, but in this case, we're going to solve a problem that's a little more complex, and it's not unlike the problem in your textbook, which talks about an electric dipole. This, in fact, is an electric dipole problem. I'm just solving it a little differently than your book did. In fact, I'm using different numbers too. So our example 3 here is a charge of negative 0.111 nanocoulombs is at the origin of an XY coordinate system. So I'm going to draw an XY coordinate system. I'm not going to show you that yet because we're still reading the question. I'm going to put the x-axis to my right, and I'm going to put the y-axis up. Okay, and I have a charge of Q at the origin that is Q equals negative 0.111 times 10 to the negative 9th coulombs, because that's what a nanocoulomb is. And then I'm going to go over 6 meters. And I'm going to put another charge, and that one's going to be positive 0.111 times 10 to the negative 9th coulombs. And then what I'm going to do is calculate the electric field at point P sub C, which is go to the right 3 meters and then go up 4 meters. So I'm going to call this spot right here the 4 point. I know I'm not showing you it yet. Right above the middle, I'm going to call that the point P sub C. Okay. All right. And the other place I'm wanting to calculate it is right above the x-axis or the origin. And that's this point up here, which I want to call P sub L. All right, so now I've written everything down, and this is what my figure looks like. So what we're asking in part 1 is to calculate the electric field there, and then in part 2 is to calculate the electric field there. Okay. So the formula for the electric field is essentially the same as the Coulomb's law, except it doesn't have that extra charge. That's the only thing you got to remember. And you just have to add to it the fact that the electric field points in the direction that a positive charge would be compelled to move if it was put in that location. And this is an electric field due to 2 separate charges, one being positive, one being negative. So what I'm going to do is I'm going to say E at C is equal to E C due to the left charge plus E C due to the right charge. So maybe I could call this one Q right and I call this one Q left. Okay. Now, what does that mean? Well, remember, just like in Coulomb's law, we learned that the force acts along a line connecting the center of masses of the doohickeys. So what I'm going to do is first off show you that we got a neat triangle here that's kind of helpful. And then the hypotenuse of that triangle is the line along which the electric field acts. So this guy's a negative charge, and this is the electric field due to it. So at this location, a positive charge would be compelled to go that way along that line. And in fact, I'm going to say that that vector is in fact the ECL. That's the electric field at the center due to the left particle. Now, if you recall, this is a 3, 4, 5 triangle. And that means this angle is like 53.1 degrees, or this angle is like 37 or 36.9 degrees. So when you look at it that way, you can see, oh, okay, well, this is clearly a vector that has a negative y component, so I'll make it red, and a negative x component, so I'll make it red. So now I got to calculate the magnitude of the ECL. That's the easy part. That's just using the formula. I got to calculate the magnitude. Then I got to use trig to figure out the components of it. So ECL is just equal to 9 times 10 to the 9th, and we'll leave off the units again, times, again, leaving off the negatives too, 0.111 times 10 to the negative 9th coulombs And this will all be over 5.0 meters squared. You can see this cancels out with this. It's 1/9 versus 9, and 10 to the negative 9th versus 10 to the 10th. So this would be 1 over 25, which I think y'all can know if you multiply the top and bottom by 4, you will get 4 over 100. So that is in fact 0.040. And in this case, we know the unit should come out in newtons per coulomb. Okay. Now, from this, I can see that the x component should be given by opposite over hypotenuse. So I can say ECL sub x would equal, forcing my negative right there, 0.040 newtons per coulomb times the sine of 36.9. If you remember the 3, 4, 5 triangle, this is 36.9 right here. You can see that the sine is opposite over a hypotenuse, so that's 3/5. When you multiply 3/5 times 0.04, you end up getting what, 3/5 times 0.04, so that would be 0.8 times 3 would be 2.4. So this would be negative 2.4 newtons per coulomb in the negative x direction, and ECL y direction would be, again, negative, I forced on it, times the cosine of 36.9. And of course, the cosine of 36.9 would be 4/5. So 0.04 over 5 is 0.8. Now I multiply 0.8 times 4, and I should get 3.2. So it's negative 3.2 newtons per coulomb. Can anybody verify any of that math? Because I'm doing arithmetic, and that's where I fall apart. Okay. All right. It looks like I did everything right. No one found the error with that math. Oh, by the way, when I calculated that ratio of F electric to F gravity last time, I noticed yesterday that I had flipped over my part of my fraction. So I was not supposed to get 10 to the 57th. I was supposed to get more like 10 to the 38th or something. So you might want to check your notes on that. I didn't make the correction on the notes because I had already uploaded them to Google Docs. All right. Now we're going to do the exact same thing with the electric field due to the other particle. And notice this one's also a 3, 4, 5 triangle. So that works kind of nice. And in this case, this is a positive charge. So this positive charge is actually going to be compelled to move that way. So this is EC right is pointing that way. And again, you still have a 36.9 degrees, but with this one, both the X and Y components, or excuse me, no, the Y component is positive, but the X component is negative. Like so. So no, like I said, I never use my trig angles, nor do I use any signs in my Coulomb law equations and stuff like that to figure out my signs. I do it all using the mechanics or the physics of it. So here we go. ECR is going to be equal to 9 times 10 to the 9th times 0.111 times 10 to the negative 9th over, again, 5.0 meters squared. This again gives me exactly the same magnitude, that 0.040 newtons per coulomb. Now I can look at that triangle a little closer, and what I see is an X component, I mean a Y component that way. So this is ECRY, and a X component this way. And of course, the total vector, the total electric field is, of course, along the hypotenuse but that angle right there is 36.9, or you could say this angle right here, which is the same as this, that's 56.1 or 53.1, sorry, degrees. So with this, I'm going to say ECR sub X is supposed to be 0.04. I'll put the negative in front of it again. That's how I force my sign, because I saw it was red there. And I'm going to multiply that by the cosine of 53.1 degrees. Cosine of 53.1 degrees is 3/5. So 3/5 times 0.04. The 1/5 times 0.04 would be 0.08, basically 0.008. And then I think I might be off by a decimal place on both of these. This might be 0.24 and this one might be 0.32. Has anybody found that to be an error yet? That might be what I did. No, okay. Hopefully I'm right then. All right, so 0.04 times the cosine of 53.1. I'll check this and that will just make sure for sure. So 0.04 times trig function cosine 53.1. Make sure I'm in degree mode. And oh, maybe I was. This is 0.024. So I was off by one decimal place, and it's negative is the x component. So yeah, I did the math right, but I should move my decimal one place to the left on this one. I told you guys, you can't trust me. I'm brilliant, and I'm also functionally illiterate at math at the same time. So like I could do really rough math calculations in my head, really hard ones rather easily, but I also make the simplest mistakes on the easiest numbers. I'll just write this over here, negative 0.32 newtons per coulomb. Okay, now the ECR sub Y, that one's actually a positive component, so I'll put the sign there, 0.040 newtons per coulomb times the sine of 53.1 degrees. Now with this one, we're going to take the sine of 53.1. Well, if I look up there at that triangle, that's 4/5. Again, the 0.04 over 5 would be 0.008, which is what I missed before. I just called it 0.08. And then 0.08 times 4 would be 0.032. So it'd be 0.032 newtons per coulomb there. Okay. So that's the actual electric field due to this one. So really the total electric field, E center, is equal to, now I'll take the x component, which is negative 0.24 newtons per coulomb, I hat, plus, or I might as well say minus, negative or minus 0.032. Yeah, I wrote it wrong over there too. No, I did 3.2, didn't I? Negative 0.32 newtons per coulomb, J hat, plus negative 0.024. Again, that's supposed to be just 0.024, not 0.024. Yeah, actually, I was supposed to have a 0 in front of that. I did it right over there, and I don't know. It's a bad day. See, this is why I don't practice work on the class, because I'm inevitably going to make a mistake. I looked at it over here, and I had written the whole number thing that I had at first. It's just, I'm an imbecile. Okay, so we got that. This is now going to become 0.024. And now you also see why I asked you guys to make sure to keep me honest. That's because, again, I'm doing stuff off the top of my head, probably not going to do it right. So the x component was the negative, and the y component on this one was the positive. So I'll say plus 0.032 newtons per coulomb, J hat, and this one was the I hat. You can see from the symmetry of this vector is going to have that guy pointing up that way, and they're identical in magnitude. So obviously one's going to have a positive y component, the other one's going to have a negative y component, and they're the same magnitude, so they should cancel each other out, which means I'm only going to have an x. And that's what you're seeing here, is you're seeing the y component negative 0.32 and the y component positive 0.32 are canceling each other out. Boom, boom. And these two just make each other stronger. So I end up getting 0. With a negative 0.48 newtons per Coulomb in the I hat direction. Okay. So that's the crux of it, how to do this type of problem. Now, the other part they said for us to do here, I think you can see what happens. I will leave it up to you to finish that part. But notice the difference here is this guy now is a triangle that has a leg of 6 and 4. So you're going to have to find that distance by using the Pythagorean theorem, square root of 6 squared plus 4 squared. And then you're going to have to use trig to figure out that angle, so you can figure out what angle this will be. So you won't get something that just has a x component like the other one did. I'll leave that up to you because I've got a bigger fish to fry that I think you'll appreciate me covering a little more than you'll appreciate this one, because it's the sort of the mother of all the types of problems. So what I want you to do first is I want to discuss with you a way of thinking about electric field in terms of vectors. And I want it specifically in three-dimensional space. Three-dimensional space can be drawn x, y, z. The main thing you got to remember with this is if you set your right hand like this, then this should be your x direction. This should be your y direction, your middle finger, and then your thumb should point in the z direction. Using your left hand, if it doesn't match that way, then you know you've done something horribly wrong. And in fact, your math will consistently come out wrong by a negative sign. So always draw your coordinate systems in what we say is a right-hand way. Really, the crux of it is I hat cross j hat is equal to k hat. If it doesn't work out that way, if hopefully you remember cross products from last semester, then you've got a left-handed coordinate system. And that causes problems in mathematics. You can deal with it. It's okay to have a left-handed coordinate system. Just all our formulas are based on right-handed coordinate systems. Okay. So let's imagine for a second that I have, let's say, a blob of matter over here. Looks like a kidney bean. And then inside of it is a little chunk of that matter that's infinitesimally small. So we can treat the center of it as if it's the center of mass of that little doohickey there, right? This is going to be a little charge element we'll call dq. And dq has a couple different forms. This is a formula you usually don't find in your book, but I allow you to use it. Everybody hear that? This is a formula you won't find in your book, but I allow people to use it. And that is dq is often written as lambda times dl, meaning it's something that's along one axis and it has maybe a constant, but it might be a functional proportionality constant, lambda. That could be a function of x or y or whatever. Another version is sigma times dA, where dA is a area element. And then the third is a charge per unit volume, dV. So charge per unit length, charge per unit area, charge per unit volume. Those are the three forms of dq we use, and these can actually be functions. You'll see today an example of how to do it, but anyways, just remember that. Then what we're going to have over here is a charge, or let's say a location P. Okay, so I'm going to create a couple of vectors on here real quick. I'm going to draw a vector that points to dq. So here's my vector that points to dq. I'm going to call that vector r sub dq. Okay. And now I'm going to have a vector that points from the origin also to P. So I'll call that r sub P, and it's nice that my pen's going to die now. And I'll just call that plain P. I ain't going to take the time of trying to write some fancy curly P. And it appears that blue does not look good on y'all's side, so I won't be using this blue much more. But everybody see those two vectors? these vectors would be how you locate dq and p in space. Now, if you thought this particular dq was the source for electric field, can you think of a vector operation between rp and rdq that would give you a vector parallel to the electric field? You're muted, Sam, in case you were talking to me.
Oh yeah, I was just going to say a subtraction between the two vectors.
Excellent. Yeah, very good. Now, if this charge is positive, and that's what we're going to assume dq is positive, then you want the force of the electric field to point away from it, right? So you want the vector that points this way. So if you look at that, you probably realize, oh, that's rp minus rdq. So this vector right here is rp minus rdq. That's a wonderful thing. Now that we have that, we have a vector that represents the real vector and the electric field direction. So the magnitude of this is actually the d that goes in d squared in Coulomb's law, which, by the way, the E form of Coulomb's law is also called Coulomb's law. So now what we can write is we can say that the differential element of the electric field with a vector symbol on it is, and now I'm going to immediately stop using that K because I told you I hate that K and nobody in the world uses it. It's going to be dq over 4 pi epsilon naught. That's actually what K is. Okay. And epsilon naught, by the way, is 8.85 times 10 to the negative 12th. And that's Coulomb squared per Newton meter squared. Now, the kicker is we need a direction. Well, the direction should be RP minus RDQ. But if I took the magnitude of RP minus RDQ and put it down here squared, like the formula tells us, I would be off by a factor of RP minus RDQ. So I actually have to put it cubed down here. So I'm going to say RP minus RDQ cubed. It's still a 1 over r squared law, but because I multiplied it by this increased the force by r, basically a d that we had in the original formula. So I had to divide it by a third d to get rid of that. This is the vector thing that you should definitely have on your equation sheet that is not in your book. These two things are quite important. Okay. Now we've got what, 18 plus 5, 23 minutes left. That's probably a good amount of time. So I'm now going to make use of that equation, and I'm going to show you how to make use of it. Okay, it's not as scary as it sounds, but this is going to be the mother of all integrals, and you're going to go like, oh crap, I'm going to fail. Everybody does that. That's this first day. Okay, but it's going to be fine. Trust me. I'm going to teach you how to do it. Everything will work out. So what I'm going to imagine is a uniformly distributed charge that's lying along the y-axis. There's my x-axis. There's my y-axis. Now what I'm going to do is hide this blue pen because it's constantly being in my way and wanting to be used. And I'm going to take right here and say, oh, I'll do the blue one. That's right. Okay, I'm going to say my charge distribution is this. It's infinitesimally thin, but I'm drawing it cylindrical with some dimension to it just so you can see what I'm talking about. So it's a wire that goes to infinity that side and to infinity that side. Now I'm going to go over here at some point, even though it's along the x-axis, I'm just going to call it z so you don't get confused and think you got to integrate it or something crazy stuff like that. So that's some distance z away. And what I'm going to say is that this thing is charged such that, this is a neat mathematical symbol that the mathematicians use. This means such that lambda, which equals dq over dl, is a constant. what that means is I would not say this in an actual problem. I would tell you this is a uniformly distributed charge on an infinite line of charge. So for instance, if you took out 3 centimeters and you determined that it had 2 coulombs in it, then any 3 centimeter section would have 3 coulombs in it. Okay, that's what that means. What I want to find now is what is the electric field here. And I'm going to find it vectorially. Okay, so what we just learned, because Mr. Younger was so nice to give you that cool new formula, what we just learned was that the differential element of the electric field is equal to dq over 4 pi epsilon naught rp minus r dq. Oh my God, it's giving me a headache already. Cubed times rp minus r dq. That just looks like the worst thing ever. Like, I don't want to integrate something that god awful scary, right? But watch, divide and conquer, easy peasy. I need a vector rp. Remember in our diagram, rp was the vector that pointed from the origin to the point at which we don't wish to know the electric field. So can anybody tell me what the vector rp is? Can anybody tell me how long it is? Points from the origin to the point at which we wish to know the electric field.
Wouldn't it be like the Pythagorean of the coordinates of P?
Yes, but do you see where P is on this diagram? That little dot right there.
Oh, it's just the X. The X value then.
Sorry, it is still kind of blurry so it's hard to
sorry.
see.
Yeah, that might be an issue too. So yeah, if you look here, this is really where P is. So RP is this vector right here. And I think y'all can now tell that that would just be Z I hat, where Z is a constant. Okay. Now I'm going to imagine a little bit of charge element right here, dq, which is actually equal to lambda times dy, because this width right here to here, that thickness is dy. And of course, it's up a height y, okay? And not only is it up a height y, that vector right there is, in fact, the vector r dq. I don't know why I put a vector symbol on there, but here we are. So anybody want to tell me what r dq is? Anybody know the length for that particular point in time?
Be dy.
That's the actual size of dq.
Oh, okay.
But the vector that goes from the origin to that dq is just y, right? You see its length is just y, and it points along the y-axis. So I'm going to call that y and then j hat. Okay. And Jacqueline, I did not see your chat asking about the negative component of x. Did you figure it out on your own, or do I need to go back and look at that? Sorry about that, everybody.
It's all good. You can get to at the end of the class.
Okay, no problem. All right, so now that we've got this, we've got the vectors. Now I just have to start computing formulas. It's amazing how easy this part is. In fact, you can go ahead and draw RP minus RDQ if you wanted to, because RP minus RDQ points from RDQ to P. And of course, it's a lot easier to say than it is to draw, especially when the paper moves right as I get ready to do it. We're going to say that was a win. So that's our vector RP minus RDQ. And I think you can tell RP minus RDQ is really a vector that has a Z X component, so Z I hat, and a negative, because I got to go from here to here. So I got to go down Y. So that's going to be minus Y J hat. Everybody agree? Of course, you could just subtract them and you'd automatically get the same formula, z I hat minus y j hat. But you can also just look at it as the vector that goes down by y and then to the right by z. Now, we also have in here the magnitude of it that we got to calculate, but you can probably look at that and tell what it is. But either way, I'm going to do it. RP minus RDQ magnitude is equal to square root z squared plus y squared. Does that make sense to everyone? They're perpendicular directions, so the Pythagorean theorem applies. Okay. So believe it or not, we're actually ready to integrate now. So E is going to equal the integral of DE, which is going to equal, notice we've already said what DQ is. DQ is lambda dy. So I can take the integral 1 over 4 pi epsilon naught, putting that out in front. I can take the integral of lambda, which is also a constant, times dy over. Now I've got to raise the distance to the third power. So I'm going to cube that. So that would be z squared plus y squared to the 3/2 power. And then this will be times z I hat minus y j hat. Now, I've written this after the dy. That's what we do. We do it sort of fast and loose in physics, but it doesn't mean you don't have to integrate it. You do have to integrate that part. Okay. So this will actually break down, and I'm going to actually integrate it from negative infinity to positive infinity along the y-axis. Okay.
What is raised to the power? Is z squared plus y squared raised to what?
The 3/2
3/2?
power.
Okay.
Yeah, 3 over 2. Okay. So this ends up becoming 1 over 4 pi epsilon naught. Actually, let's go ahead and write the lambda in there. Lambda over 4 pi epsilon naught times integral of z over z squared plus y squared to the 3/2 I hat minus integral. So I'm factoring out all this stuff minus the integral of, and actually this was supposed to be dy was supposed to be there. This one be minus y dy. The lambda's already been pulled out. I've got the minus there, so I don't need to put it here. And this will be over z squared plus y squared to the 3/2 power, and that'll be in front of a j hat. Okay. Now this goes from negative infinity to positive infinity, negative infinity to positive infinity. What you might notice is if you replace y, which is the integrand, with negative y, you'll see that this second integral is in fact what we call an even function. Y'all see that? Actually, it's an odd function. Sorry, I misworded. I was thinking I was doing the other one. If I put a negative y in here, I'll get negative y. Down here, I'll just get y squared again. So the integrand becomes the negative of what it was when positive. So since it's odd and we're integrating over symmetric range, we already know from mathematics that this should go to 0. But we also know that from the physics of the problem. Notice when we're talking about this point y, the electric field points like this and has a negative y component and a positive x component. Now, if you go to y this way, negative y, in other words, now you got the exact same vector, except the y component is reversed. So this y component is going to cancel out that y component. Is going to do it for every possible y. So you expect it to be 0 physically. But what I said was mathematically, it's because it's an odd integrand and an even interval, or symmetric. So you really don't have to compute that integral at all. So let us stop for a second and compute the other integral. Notice the z is a constant. So I'm going to say lambda z over 4 pi epsilon naught integral dy over z squared plus y squared to the 3/2. That's all that's left now since this integral's gone away. And that goes from negative infinity to positive infinity. But we see that that's not necessarily a wonderfully easy integral, but hopefully you guys recall your techniques of integration really well. This is perfect for, anybody know?
Trigonometric substitution.
There you go, trig substitution. So let's say, let u equal, let's let y equal, or let's let u equal y tangent theta. Then du is equal to y secant squared theta d theta. Okay. Wait a second, that's not what I want to do either. No, that's not what I want to do. Sorry about that. That's weird. I do this like off the top of my head all the time, and I just had a brain fart on it. But yeah, it is trigonometric substitution. What we want to do is we want to exchange this. So basically what we're going to have is we're going to say y equals z tangent theta. That's what it is. Let y equals z tangent theta, then dy is equal to z times secant squared theta d theta. I don't know what happened to my brain just then, but anyways, it's supposedly fixed at this point. Okay, so we've already got the dy there. That's the nice thing. But look what happens now that we do that. We can say, okay, this integral now becomes lambda z over 4 pi epsilon naught integral. I'm going to leave the range off right now. The y is going to become, the dy is going to become z secant squared theta d theta. Z squared plus y squared is going to become z squared plus z squared tangent squared theta. But all that's going to be to the 3/2 power. And that allows me to factor out the z squared. The z squared under a 3/2 means the 2 in the bottom is going to cancel out with the 2 in that, and then it's going to be replaced with a 3. So I have a z over z cubed, which would be a 1 over z squared, and that's going to cancel out that with leaving just one z in the bottom there. So I'm going to have lambda over 4 pi epsilon naught z. Now what's left is getting rid of all that. I have secant squared theta d theta over 1 plus tangent squared theta to the 3/2. And of course, you all know what 1 plus tangent squared is, don't you, from your trig identities?
Secant squared theta.
Very good. So now we've got secant squared theta over secant squared theta, but secant squared theta is raised to the 3/2. So it's secant cubed theta, really. So this part right here is just secant squared theta, but that square is going to cancel out with 2, leaving a 3. A 2 on top and a 3 on the bottom means a 1 on the bottom. So I'm just going to have lambda over 4 pi epsilon naught integral d theta over secant theta. And of course, secant theta is 1 over, or excuse me, did they all cancel out? No, yeah, we got 1 in the bottom. And secant theta, of course, is just 1 over cosine. So I get lambda over 4 pi epsilon naught integral cosine theta d theta. Now, here's the tricky part. What's the range of integration? Well, this is really wonderful. The z equals y tangent theta, or y equals z tangent theta, because that means there exists at least some idea of a triangle where the tangent of theta, which is opposite over adjacent, is in fact opposite, which is y, over adjacent, which is z. And in fact, this part would be z squared plus y squared. Okay, notice tangent theta equals opposite over adjacent, so that gives you exactly what you want. And you see, as y goes to infinity, theta would go to 90. So y going to infinity implies theta goes to 90 degrees, or of course pi over 3 or pi over 4 or whatever. And then y going to negative infinity implies theta goes to negative 90 degrees. So that works. That's one way you can think about it. Another way you could think about it, of course, is you could also just realize that this is just getting infinitely large. So this angle is going to try to stand straight up and you'll get 90 degrees again from that way. Okay. So we can go ahead and do this now. We also happen to notice that cosine is an even function, and we could instead do 2 lambda over, or excuse me, do lambda over 2 epsilon naught. Sorry about that. No, I'll leave it there. 2 lambda over 4 pi epsilon naught times the integral from 0 to 90 degrees of cosine theta d theta. Because this cosine theta is an even function. Remember, it's symmetric. Like that. So we're integrating over a symmetric range, which means you can integrate from 0 to the same point and just double the answer. That's why I put a 2 there, and I lost my z somewhere. Z was there, but it disappeared here and here. Everybody put that z back in. Evidently, I messed it up, and that z should also go here. So now I get finally lambda over 2 pi epsilon naught z. And then, of course, the derivative of sine is cosine. So the integral of cosine is sine. Sine of 90 degrees is 1 minus the sine of 0 degrees, which is 0. So I end up getting just 1. So that'd be lambda over 2 pi epsilon naught z. And in fact, our electric field is now, remember, it had the I hat in front of it before I just started working on the integral itself. So now I have lambda over 2 pi epsilon naught z, and that should be pointing in the I hat direction. That's it. That's the mother of all integration problems. Okay. Now, I like this problem. I like working it out like that, and it tells us a neat thing about an infinite line of charge. It only falls off as 1 over z as opposed to 1 over z squared. That's actually the same reason we use fluorescent light tubes in a ceiling. You know, those long tube lights that you have in a ceiling or in a store or something like that. By making it a long tube light instead of just a incandescent circular bulb, the circular bulb has the brightness of the light fall off like 1 over r squared. So if you're 3 meters off the ground, you're actually about 9 times, or let's see, yeah, about 9 times dimmer at the floor than you are at 1 meter below the bulb, which is roughly where your head is, right? And if you do that with a infinitely long light, then you're only going to be down by a factor of 3 instead of a factor of 9. And in fact, if you make several of them next to each other, it starts to approach a plane. And later, when we do the calculations of integrals over the electric field to find the electric field over an infinite plane of charge, you'll see that that has no z dependence. So there we go. I am going to spend some more time next time doing a couple more integrals from chapter 21. And no, you guys meet Monday. Yeah, we'll still do that because you meet Monday and then we're supposed to do 22. So we'll be a little bit behind. If I see that I'm so behind that chapter 22 or 23 will be due earlier than you've done it, than you've covered it, then I'll move the homeworks back, all of them at that time, but I shouldn't have to. Someone have a question here, Victoria or Alexi?
Oh, No, sorry, I wasn't sure if I heard you right. You said that we meet Monday. I just wanted to remind you that Monday's a holiday.
Right. Yeah, we're not meeting Monday. Yes, that's correct. That's what it was screwing me up. I was thinking we were meeting Monday and Wednesday of next week. Actually, I was thinking we were meeting Tuesday and Thursday of next week, but that's definitely not the case. So I'm still going to do another problem, but I definitely recommend you looking up at some of the problems I did on my YouTube channel. I sent out an email today about updated the syllabus to get rid of some typos and other problems. I updated the list of videos. Just scroll past the astronomy ones. I should really put it as physics first, but I haven't yet. So just scroll past the astronomy ones and look for ones where I'm using Coulomb's law and integrating. Okay, you'll see this one's been worked maybe 3 or 4 times on there. What I can do to this type of problem for a test that's nice is I can actually make this go down to L, say, and this one go up to 2L. Then it's not symmetric anymore. And you're not going to get the y components, or excuse me, the y components canceling out. I could also let L be, k times y, or some other constant. I'm not meaning the k that we were using earlier today, just any constant times y, or I could let the lambda be some constant times y squared. There's all sorts of ways I can juice this up to make it slightly different, but to test you on whether you know how to do this. And then I can just ask you questions about this, okay? But this is not one of the formulas that have allowed you to put on your equation sheet. So this is an integral you need to be able to do. Like I said, I've done it a lot of times. I've probably got 4 recordings of it on my YouTube channel. So check those out, but I've got other ones too. You'll see in your book, it does a loop of charge, and you'll see that it does a plane of charge as well. I'll do those next time just to make sure we get them done. And then I'll go into Gauss's law. So y'all might want to go ahead and watch Gauss's law videos too. Everybody's free to go. Thanks for coming, everyone. I'll put this document up probably tonight, and the video will probably go up tonight too.
Can you go over how to find that x component?
Yes. Okay. So we're looking at, was it this part of the problem?
Yeah, just I got the rest of it. It's just that some of my house was trying to get my attention. I had to step away for a moment.
Okay, gotcha.
It was just determining which way the x component was either positive or negative.
Okay, so when we were talking about just this charge causing an electric field here,
Mhm.
what we imagined was putting a positive charge here, and that positive charge would be attracted to that negative charge. So that positive charge would want to go this direction.
Oh, okay.
So if I wanted to go along this vector from tail to head, if I first went along the y-axis, I'd have to go down, and then along the x-axis, I'd have to go to the left. Down is the negative y direction, and to the left is the negative x direction.
Okay, so we can always assume that the unknown, we can just make it positive and determine direction.
To determine the direction of the electric field, yeah, that's what the definition of the electric field direction is the direction that a positive charge would want to travel.
Gotcha. Okay, that's where I got a little confused at. Like I said, some of my house was trying to get my attention. I had to step away for a minute.
No problem. Yeah, so in this case, this is the other one. This is one that was probably stumping you a little bit, but that's a positive charge. If a positive charge was here, it wouldn't want to go that way. And the only way I can go from here to here is I go to the left, which is a negative x direction, and I go up, which is a positive y direction.
Because they're retracting. Okay, I got it.
Sense?
Yes, totally.
Okay, and that's the way you do all these. It looks scary when you see that god-awful integral formula I gave you, but that integral formula is really a lifesaver. They make you do this in upper level undergraduate courses, and a lot of books don't give you this way of doing it, and it's terrible because it's really hard to work through this unless you have some kind of regimen to follow, and that's what this provides you, is just, hey, find the parts.
Yeah, I go to ODU, and I'm taking this class right here to make it a little bit easier on me.
Yeah, I really try hard to make sure I explain all the gory details.
No, and I appreciate
think that helps people.
Yes, definitely, and I appreciate that.
Thank you. Well, you have a good one. That was
too.
cadmium, right?
No, it's Jacqueline.
Yeah,
Yep.
sorry.
No, thank you.
No problem. Have a good one, Jacqueline.
You too.
Anybody else have any questions? Cadmium? Go ahead.
I do, sir. For some reason, your class is not available to me on Canvas at all. Like my lab class is up there and my Calc 3 class is up there, but your class is not showing up for me at all. And I'm unsure if this has to do with the matter from last semester as well.
Gotcha. Darren, do you see my course? Since Darren's still in here. Maybe Darren's not here. Okay, I'm not sure why that's the case. Let me make sure you're listed in my course. So this is cadmium, and this is the NO5B section. I'm going to check SIS real quick and see what it's got you listed as.
There's an SIS.
You're definitely supposed to be in there. And
In my SIS, I am enrolled in this class, but I'm not sure what's going on what's happening.
Okay,
Because I do have an I for incomplete for physics 1 with you.
gotcha. Oh, I bet you that's the problem then. They might have bumped you just because you haven't made up that incomplete yet. And you sent me an email on that too, didn't you?
Yes, sir.
Yeah, I saw it yesterday. I hadn't had a chance to get to it, but I will definitely address it immediately. And I think we'll be able to do something with
Okay.
that. Probably next week, if that's okay.
That works as well, as long as it works for you, sir.
Yeah.
But
We
if
have until the
homework is
18th to
due
add
on
you,
Monday,
so-
then can I get an extension on the homework?
I might be able to do that. Yeah, on this case, one case basis, I might be able to do that. I'm looking right quick to see if they dropped you from the class. My schedule, here I am. Okay, so we got to get this done. They probably won't let me put you back in here. Yeah, it's got you listed, but it's not showing you. Are you accidentally try a different browser because your cache might be remembering your TCC? I mean your ODU. Aren't you? You're at ODU too, right?
I am an ODU student taking classes at TCC. Yes, sir.
Yes. So what I'm wondering is if your cache is not bringing you to your SIS from there as opposed to from here.
Well, ODU doesn't use these websites. They tend to use Blackboard and Leo Online.
Okay, so they don't use Canvas then. Okay, so
No,
that's going to
sir.
be the problem. Yeah, that's weird. I don't know. I'm going to send an email to Canvas Help, and maybe they'll be able to help you immediately, or they'll get to it first thing tomorrow, and I'll find out what I can by then too. Okay.
Yeah, I just opened it up on another internet browser and it's still not showing up, so that's not the issue. Thank
Yeah,
you,
that's
though,
weird.
sir.
It's showing you right there in it and everything. So that's weird. Let me check my grade book and see if you're actually listed in that as well. Because SIS is supposed to feed to Canvas, but it's not necessarily a everyday thing. They might have dropped you and not dropped you out of SIS yet. Let's see. So look for today or tomorrow morning, look for an email from me regarding doing your makeup stuff. What I'm probably gonna have to do is open up. Did you miss the midterm and
Just
the
the
final?
final
Or just the
exam. I
final?
submitted all of the other work though.
Okay. Yeah, it's got you in here too. So it's definitely showing you in here. What I'm going to try to do is I'm going to get that course open so you can do your practice tests some more to practice for the final. And then I might be able to set up where you take the final by Respondus or something. But I'm going to try to
Okay.
find out how to get you in here. Okay.
Thank you so much, sir. You have a lovely day and a lovely weekend.
You too. Take care, Cadmium.
Bye.
Bye-bye. Darren, I haven't heard. Oh, there you go. Gotcha. So Darren's having technical problems with his mic. I'm going to check my email to see if you sent me anything that I can act upon right now. I do not see an email from you, Darren. I will watch for the email, but you may also try to text me if you like, since I think you're here and still can hear me. Look on my syllabus and you'll find my phone number. You can text me if you'd like, if you need a more quick response. I'm going to go ahead and kill the class. Have a good one.